We're going to be working on this lesson here for limits and asymptotes. So you will need to gather together anything you want to write on. So however you've been taking notes for this semester, and you do need to have a graphing calculator. If you are using the app, just make sure that you're able to split screen, or that you make sure you know how to use that graphing calculator. It will be assisting you throughout this video. All right. So we're going to start with what is a vertical asymptote, or where do they occur? So go ahead and remember, I just want to remind you, you can pause at any time. In the next couple of slides, I'm actually going to insist that you pause so that you can write down the examples. But here, remember, you can pause if, because I'm just going to speak fluidly, and that way you'll be able to stop when you need to catch up with the notes. All right, so vertical asymptotes. What are they? Where do they occur? Why do we even have these things? You can remember graphically that a vertical asymptote is drawn as a dashed line. And we may see functions that kind of ride close to that asymptote. Maybe this one would come down this direction. Okay, so this is a place in which the graph does not exist, or the function. So our function does not exist. Okay, so the x value is not a part of the domain. So there's another way we can look at this. The excluded value from the domain. Okay, so when we are talking about, and it doesn't mean that every time something is excluded from the domain there must be an asymptote. That's not the case. However, these types of functions that we're going to work with, which are called rational functions, and the reason I think it's important to know that they're called rational functions is because if you were to go and try to get some extra practice on your own, or if you were to want to speak to someone, a math teacher about this and seek some extra help, to use the correct language is going to get you so much further. So if you look up rational functions, you're going to get all sorts of these examples that it can give you some extra practice. If you were to have a conversation with a math tutor and you say, well, I'm working on vertical asymptotes of rational functions, so that's why I'm going to call them by their accurate name, and hopefully you will choose to use the accurate name. So rational functions are functions that are written in a fraction. One example would be if I had f of x equals 2 over x minus 4. So that's just an example of a rational function that would have an asymptote. Well, why does it have an asymptote? Because there's going to be an excluded value from the domain. There's going to be a value in this particular function in which the function won't exist because an x causes the denominator to be 0. So that's our issue. So we've actually talked about limits when we can't put in a certain value. So let's take a look here at some examples, and just to identify where the vertical asymptotes exist. So just where do they exist? I'm not going to do anything calculus-wise. This is actually an Algebra 2 topic. So here I'm going to insist that you go ahead and stop the video, pause it, and write down those 5 examples, and then come back and we will work through them. So go ahead and pause now. All right, so you've unpaused and you're back with me, and we are going to take a look at these examples. And I don't like blue on this slide. We'll go with green. And so for each of these examples, we are just identifying where that asymptote exists. Maybe there's multiple asymptotes, because we want to be able to identify that there's going to be an issue with approaching that asymptote. That's like the whole purpose, is we're getting to limits here coming up. So for number 1, we would look at the denominator and we would say, well, x cannot be negative 4. So we know that a vertical asymptote exists at x equals negative 4. We are going to write it as x equals negative 4 because soon enough we'll be talking about horizontal asymptotes, which are y equals a quantity. So it is, we're going to differentiate those. So this should be x equals and then the number. Okay, let's take a look at the next one. So in order to approach this one, we would want to factor. So I'm going to do x minus 4 and x plus 1. I'm only looking in the denominator. However, I notice that the numerator is x squared minus 16. And x squared minus 16 also factors with an x minus 4. So because that cancels, it is not. So anything that cancels is not a vertical asymptote. So not a VA, a vertical asymptote for abbreviation. However, we still have this one right here, which would lead to a vertical asymptote existing somewhere else. So my vertical asymptote is at x equals negative 1, because if we use the negative 1, the denominator would become 0. Where it cancels out is not a vertical asymptote. It's actually called a hole, if you can remember that from Algebra 2. Okay, so I'm on to the third example. This one's pretty straightforward. I'm just going to take that denominator and set it equal to 0, and that is where my vertical asymptote exists. Okay. Looking at number 4, I'm going to take the denominator, and I'm going to set it equal to 0. You say, well, why don't you factor it? Truthfully, it can't factor. So maybe I would try to subtract, and then I'd go, wait a minute. I can't take the square root of negative numbers. Oh, but my Algebra 2 teacher said I could. Yes, I could. We would get positive and negative 3i. However, those are not locations on our coordinate plane. Like, where would you put negative 3i on the coordinate plane? So if you can't graph it on a coordinate plane, then it's not a location of an asymptote. So in this case, there are no vertical asymptotes at all because we don't get any real values of x. We get imaginary ones. All right, let's take a look at this last one. So once again, I'm going to go ahead and factor the denominator, and I can take out a 3 as a GCF, and then the numerator would be t plus 1 and t plus 1. So I do see that that will cancel, and then I end up with just t plus 1 over 3. But since 3 doesn't equal 0, there's no variable left, that this one also has no vertical asymptotes. All right, so I'm going to leave that there. So make sure if you need to pause, you can check all your answers for those 5 problems. And when you're ready, you can go ahead and move on with me. All right, so once again, I'm going to suggest that you go ahead and copy down those 5 examples. So pause it and write them down, being careful to note some of these are left-handed and right-handed limits. Okay, so you're back, and we're going to go ahead and take a look at each of these individually. So for a limit that is not a left-handed or right-handed limit, but it's just a general limit, we know that this is approaching 3. We're trying to approach 3, but it's approaching an asymptote because the asymptote exists at 3. So if we are trying to approach the asymptote, then one side is going up, the other side is going down, or they're both going up or they're both going down. However, they'll never meet. So we would actually say does not exist, okay? Not existing. They're never going to touch because there is this dashed line in which they will, no, in this case, actually one side goes up and one side goes down. But either way, they're never touching, so it doesn't exist. Number 2 and number 3 go together. Numbers 2 and 3 are addressing approaching the asymptote at x equals 2. So we know that there is a vertical asymptote at x equals 2 for both of these problems. It's the same problem. However, I'm trying to approach it from the left and from the right to see which side goes up, which side goes down, or do they both go up, do they both go down to positive or negative infinity. So if I'm trying to approach this from the left-hand side, then I'm looking at a number. So I'm going to try to picture a number line. And I'm approaching 2, trying to approach 2. Then I'm choosing something on the left side of 2, which means I might be choosing something like 1.99999. Now, I really want to get super, super, super close to this, but I'm choosing a number less than 2, so smaller than 2. So think about putting that in. If you put in the number 1.99999 plus 5 into the numerator, you get a positive number. Now you can actually write the number 6.999, but I think it'd be better for us to picture that the numerator is going to be positive when I use a number and I'm adding 5 to it, okay? The bottom, if I choose a number that is less than 2, 1.99999, less than 2, minus 2, then I have a negative denominator, which means that ultimately I'm going to have a positive divided by a negative, and that this is going to negative infinity, okay? On number 3, we are going to choose a value on that number line that is on the right side of 2. For example, I'd be choosing the number 2.0000001, okay? I'm just choosing a number bigger than 2. Well, if I substitute a number bigger than 2 into the numerator and I add 5, I get a positive. And if I put a number bigger than 2 in the denominator and I subtract 2, I still get a positive. So this one is going to positive infinity. Okay, now on the next example, I'm going to use a calculator to assist me. Not because I think it requires a calculator, but because I think some of you may appreciate just seeing how we could do this with a calculator, because maybe that was very abstract for you to think about plugging in a number and considering it just positive or just negative. So let me give you a little bit more concrete and use my calculator. So I'm going to split my screen here, hopefully successfully. All right, and let me get back to my home screen. There we are. Okay, so looking at number 4, I'm going to approach 4 from the right-hand side. That means numbers that are bigger than 4. For example, I'm going to choose the number 4.001. Okay, so in the numerator, I'm going to open parentheses, and I'm going to put in 4.001 minus 3. And then I'm going to close my parentheses, press divide by, and in the bottom, I'm putting the quantity of 4.001 minus 4 quantity, and then I'm going to hit the squared button. So I'm typing it exactly as I am picturing it. Something bigger than 4, but close to 4, right? Like I don't want to choose a number 7. I want to choose something super close to 4 because we're trying to approach it. Now, if I press enter, I get a positive number, okay? Actually a pretty big number. So this one is approaching positive infinity. I'm going to go to number 5, which is coming at 4 from the left. I'm going to repeat the same thing, but I'm going to use a number slightly smaller than 4, like 3.999. Think of money. $3.99 is less than $4. And then you can go on the other side of that, and $4.01 is bigger than 4. So I'm just adding extra zeros or extra 9s to make it super, super close. Okay, so I'm going to retype that as 3.9999, okay, doesn't matter how many you do, just be consistent, minus 3, parentheses divided by, new set of parentheses, 3.9999 minus 4, parentheses squared, equals, and I get another positive. So both of these are approaching positive infinity. So even though the left and the right are both going up, they would actually never meet because there is an asymptote at x equals 4. All right, I'm going to close my calculator and we're going to continue to take a look at these next ones. So go ahead and again pause and write down those 6, and we will work through those 6. All right, so you are back with me, and we are going to approach -3 from the right and from the left. Okay, I'm going to go a little bit more abstract on this, and I'm going to say, all right, a number that is greater than -3. Okay, this is kind of hard to think about maybe. But on the greater than -3 side, I'm choosing like -2.99. It doesn't feel like it's greater than -3, but it is closer to 0, and that's greater than. So if I put that number in the numerator, I'm going to get a negative. If I put that number in the denominator, I'm taking a negative number, I'm squaring it, so itself is positive. But since it was smaller than 3, when I square it, it's going to be less than 9. So it's going to be something smaller than 9 minus 9. So I don't know how to, well, I can write this. Smaller than 9 minus 9, which means it's going to be negative. So all in all, this is going to turn out to be positive infinity because a negative divided by a negative is a positive. Let's go on to number 7, which is approaching negative 3 from the left side, which means that I'm on this side of negative 3, for example, negative 3.001. Once again, the numerator is going to be negative because 4 times a negative is negative. And then the denominator. Now you have something bigger than 3 squared, negative 3. But when you square it, it's positive, but it just got bigger than 9. So my denominator is going to be positive. So ultimately, this approaches negative infinity from the left-hand side. All right, so I am going to want you to just pause the video, and then when you unpause it, I'm going to just display the answers for the next one. So I want you to try them. I want you to try 8, 9, 10, and 11, and then just come back to me when you're ready to verify your answers. Okay? Okay, so for number 8, we are looking at positive infinity. For number 9, it is negative infinity. For number 10, negative infinity. And for 11, positive infinity. So if you have any questions on those, make sure that you bring them to class. We will do the practice on this. So there's no Math Excel right now. I just want you to make sure you feel comfortable with these notes and that if you have any questions, you're ready to ask them when we see each other again in class. Thank you guys very much, and we'll see you soon.